Hello there, and welcome to the Sleepy Space Channel. Every star in the night sky is a furnace, burning at temperatures we can barely hold in the mind. And yet the space between them is among the coldest places that has ever existed, resting only a few degrees above the lowest cold there is. It is a sobering thought that a universe filled with fire is almost everywhere, frozen near the very bottom of cold. Tonight we ask how both can be true at once and where all that starlight finally goes. We will follow the heat from a single trembling atom out to the cold between the galaxies. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who would enjoy them too. Thank you for being here. But for the next couple of hours, none of this is anything you need to carry or solve. There is nowhere to be and nothing to hold. Settle in. Let your shoulders soften. Let your breathing slow and deepen. Let the day fade gently away behind you. Let's begin. Part 1. The question in the dark. The night sky looks crowded with fire. Thousands of stars hang above us, and beyond them, hidden from the eye, lie hundreds of billions more. Each one is a furnace, burning at temperatures we can barely hold in the mind. The surface of the nearest star reaches many thousands of degrees, and its center far hotter still. The sky is, by any honest reckoning, full of heat. And yet the truth of that same sky is a quiet, sobering one. The space between those stars is among the coldest places that has ever existed. Step away from the warmth of any star, and the temperature does not fall to something merely chilly. It falls almost all the way to the bottom, to within a few degrees of the coldest temperature the universe allows. This is the strange fact we will sit with tonight. A universe lit by fire is, almost everywhere, bitterly cold. The sun releases more energy in a single second than our entire species has used across all of its history, and still the space a short distance from any star rests near the absolute floor of cold. Two things that seem as if they cannot both be true are both completely true. The stars are scorching. The dark between them is frozen. And the puzzle of how that can be is the thread we will follow, slowly, out into the night. It is worth noticing how completely this overturns the picture most of us carry without examining it. We tend to imagine space as cold the way a freezer is cold, as though there were some active chill filling it, pressing on anything that enters, ready to seize warmth and tear it away. The films show astronauts freezing solid in an instant, frosting over the moment they touch the void. None of that is how it works. There is no chill pressing in, no cold seizing anything, because there is almost nothing out there to do any seizing. The cold of space is not aggressive. It is the opposite of aggressive. It is the great emptiness simply declining to keep anything warm, because there is too little of it to hold warmth at all. And in the same breath, the heat of the stars is more concentrated, more fierce than anything our daily lives prepare us to imagine. The center of a star is hotter than any flame we could light, hotter than any furnace we could build, a fire of a different order entirely. So the universe holds, side by side, two things further apart than almost anything in our experience: a fire fiercer than any fire, and a cold emptier than any cold, and it holds them so close together that the same patch of sky contains both. The fierce point of fire and the immense gentle cold around it. That is the picture we are here to understand, and the strangeness of it is the strangeness of how heat behaves when nearly all the matter is taken away. The question hides a second one inside it, the question on the cover of this video. If the stars have been pouring out heat for billions of years, where does all of that heat go? It does not pile up. The universe is not slowly cooking itself warm. Somewhere, all that fire is being spent, spread, lost into the dark. We will trace where it goes, gently, by the end of our journey. The answer, when it comes, will not be that the heat is destroyed. Energy is never destroyed. The answer will be quieter and stranger than that, and once it is understood, the cold of space stops being frightening and becomes something closer to peaceful. For now, it is enough to feel the shape of the mystery. Hold the two facts side by side and let them rest there without resolving yet. The stars are hot. Space is cold. Between them lies almost nothing, and in that almost nothing is the whole of the answer. It is worth letting the sheer size of the contrast settle in, because numbers alone do not quite carry it. The center of the sun reaches around 27 million degrees. The dark between the stars rests at roughly 3 degrees above the absolute bottom of cold. Between those two numbers lies almost the entire range of temperature that exists anywhere, and both of them are ordinary features of the same quiet night sky. One is the temperature of a furnace that has burned for billions of years. The other is the temperature of the emptiness that furnace hangs within. They are neighbors, in a sense, separated by nothing more than distance and the thinness of space. We are not used to thinking this way, because on the surface of our own world, temperature behaves gently. A warm day and a cold night might differ by a few tens of degrees. Step into shade and you cool a little. Step into sun and you warm a little. Everything is softened, averaged, shared around by the air that wraps the whole planet in a single moving blanket of warmth. The Earth's air is a great equalizer, forever carrying heat from the warm places to the cold ones, smoothing the extremes until the whole surface stays within a narrow and survivable band. We grow up inside that gentleness, and so the savage contrasts of space feel impossible when we first meet them. But the air that softens everything is exactly what space does not have. Remove the air, and the gentleness goes with it. There is nothing left to carry warmth from the lit side of a thing to its shadowed side, nothing to fill the dark between the stars with a shared and even temperature. What remains is the raw arithmetic of fire and distance, with none of the blurring we are used to. And that raw arithmetic produces a universe of furious heat gathered into tiny points, surrounded by an enormous, even patient cold. To understand how that can be, we have to set aside the intuitions the air gave us and begin again from the very smallest scale. We begin with the smallest thing of all, the thing that decides whether anything is warm or cold, and we will build outward from there until we reach the cold that fills the space between the galaxies. There is no need to hold on to every word. The understanding will gather on its own, the way warmth gathers, slowly, without being asked. Let the question settle. The dark is not in any hurry, and neither are we. The first thing worth knowing is that the cold of space is not what most people imagine it to be. It is not a wind. It is not a force that presses inward, searching for warmth to steal. There is no icy current in the vacuum, no chill that reaches across the dark to find you. The cold of space is something far simpler and far stranger than any of that. To understand it, we have to understand what heat itself actually is, and that is where our slow walk begins. Part 2. What heat really is. Temperature is not a substance. This is the quiet idea at the bottom of everything we will explore tonight, and it is worth letting it settle fully before we go on. Warmth is not a thing that fills a space the way water fills a glass. Cold is not a thing either. Both are descriptions of something much simpler and much smaller. Temperature is a measure of motion. Everything that has a temperature is built from countless tiny particles, the atoms and molecules that make up all matter. And those particles are never perfectly still. They tremble and vibrate and rush about, always, even in things that seem completely solid and quiet. In a warm object, those particles move quickly, jostling and colliding with energy. In a cold object, they move slowly, their motion damped down towards stillness. Temperature is simply the average of all that unseen motion. That is all it has ever been. When something feels hot to the touch, what is happening is that its fast-moving particles are hitting the slower particles in your skin and handing their motion along, particle to particle, until the warmth has passed into you. Warmth, once we see it this way, is always on the move, always flowing from where there is more of it toward where there is less. A warm thing set beside a cool thing will always share its motion outward until the two come into balance. The fast particles of the warm thing nudging the slow particles of the cool one into quicker motion, while their own motion slows. Heat flows downhill, in a sense, always from the warmer toward the cooler, never the other way on its own. This is why a cup of tea cools and never warms itself in a cool room, why a warm hand can thaw a cold one, but a cold hand never chills itself further by touching a warm one. The warmth always spreads from where it is gathered toward where it is thin, evening itself out wherever it can find a path. This means that to have a temperature at all, a thing must be made of particles that can move. Warmth lives in matter. It lives in the trembling of atoms. Take away the matter, and there is almost nothing left to be warm or cold, because there is almost nothing left to move. This is the first key that begins to open the whole puzzle. When we ask why space is so cold, we are really asking a question that hides a deeper one underneath it, because space is very nearly empty, and a thing that is empty has almost no temperature to speak of in the ordinary sense at all. There is something else worth holding here, because it changes how we picture the cold. Cold is not an active thing. There is no coldness that pours into a warm object and chills it. What happens instead is that heat drains out, and what remains is slower and slower motion. The cold is simply what is left behind when the warmth has gone. A warm stone left out on a winter night does not have cold poured into it. It gives its warmth away to the dark air around it, and as the motion of its particles slows, we call what remains cold. The cold was never added. The warmth was only subtracted. Carry this picture out into space, and the meaning shifts in a way that is almost gentle. A warm object floating far from any star is not being attacked. Nothing is reaching in to chill it. It is simply releasing its own warmth, letting the motion of its particles slow, finding nothing out there in the dark to give the motion back. The cold of space is not a presence. It is an absence. It is the near total quiet that remains when there is almost nothing left to move. This is why the old image of the icy void, the freezing wind of space, is not quite right. There is no wind, because there is almost no gas to blow. There is no chill pressing inward, because cold cannot press. There is only emptiness, and the slow loss of warmth into that emptiness. Space is cold the way an empty room is silent, not because something fills it with silence, but because there is nearly nothing there to make a sound. The quiet is not a thing. It is what remains when the things are gone. It helps to picture the motion directly, because it is easy to say that particles move and harder to feel how ceaselessly they do it. In the air of an ordinary room, The molecules are flying about at speeds of hundreds of miles an hour, colliding with one another billions of times every second, ricocheting in every direction in a blur of motion too fast and too small to see. That frantic, invisible storm is what we feel as the gentle warmth of a comfortable room. Warm it a little, and the molecules fly faster and hit harder. Cool it, and they slow. The temperature on a wall thermometer is simply a steady readout of how vigorously that unseen crowd is moving, averaged over countless particles at once. Now imagine slowing that crowd down. As a substance cools, its particles move more sluggishly, collide more softly, settle toward stillness. Take away enough motion, and a gas becomes a liquid, its particles no longer flying free, but sliding past one another. Take away more, and the liquid becomes a solid, its particles locked into place, trembling rather than roaming. Cold, at every step, is simply less motion. There is no point at which something cold is doing anything extra. It is always doing less, moving less, until at the very bottom the motion has nearly all been removed and almost nothing stirs at all. This is why the warmth of your own body is not a thing you possess so much as a thing you are constantly making and constantly losing. Your body runs warm, its particles kept in brisk motion by the slow fire of the food you eat, and it is always shedding that warmth into the cooler world around you, into the air, into the chair, into every cooler thing you touch. You are a small, steady source of heat, leaking warmth outward in every direction, at every moment, and replacing it from within just as fast. Carry that same warm body out into the emptiness of space, away from the air and the chair and every cooler thing, and the leaking does not stop. There is simply nothing left to leak into but the dark, and nothing out there to slow the loss. Hold that for a moment. The cold we are chasing is not a force. It is a stillness, the stillness of particles that have slowed almost to nothing because there is nothing around them to keep them moving. And that means the real question is not why space is cold, but why anything in it is ever warm at all, and how that warmth manages to travel across the emptiness from a star to a world. To answer that, we have to look more closely at the difference between two things people usually treat as the same: the difference between how hot something is and how much heat it can actually give. Part 3: Hot and yet almost empty. There is a difference between temperature and heat, and it is one of those quiet distinctions that, once seen, dissolves much of the mystery on its own. Temperature, as we have said, is how fast the particles in a thing are moving on average. Heat is something related, but different. Heat is the total amount of that energy a thing carries, and how much of it can actually flow into you. The two usually go together in everyday life, which is why we rarely notice they are not the same. But out in space, they come apart in a way that is strange and important. Imagine a single particle moving extremely fast. By the strict measure of temperature, that particle is scorching hot, because temperature is about speed of motion, and it is moving with enormous speed. And yet, if that single particle struck you, you would feel nothing at all. It carries almost no energy in total, because it is only one particle. Now imagine a great crowd of such particles, packed close together, all moving fast. That crowd could burn you instantly, because there are so many of them, each delivering its share of energy. Same temperature, wildly different heat. The difference is not speed. The difference is how many particles there are to deliver the warmth. We meet this difference every time we see sparks fly from a grinding wheel or a sparkler on a winter night. Each spark is thousands of degrees, genuinely hotter than boiling water, hotter than molten metal. and yet the sparks land on the skin without harm. They are so tiny, each carrying so little total energy, that they cool to nothing before they can do anything at all. They are hot by the measure of temperature, but they hold almost no heat. The same principle, written across enormous scales, governs the temperature of space itself. There is another way to feel this difference, one closer to home than the stars. The thin wind of particles that streams outward from the sun, washing past the Earth and on through the whole solar system, is measured at temperatures of many thousands or even hundreds of thousands of degrees. By the strict measure of how fast its particles move, that wind is searingly hot. And yet it does not scorch the spacecraft that fly through it, nor the upper edges of our own world that it washes against, because it is so unimaginably thin. Its scorching particles are spread so far apart that only a scattered few ever strike anything at all, and those few carry so little total energy that they cannot warm what they touch. A wind hotter than any furnace blows past us constantly, and it is harmless because there is so little of it. This is the lesson worth carrying out into the rest of the night. Temperature, on its own, does not tell you whether a thing is dangerous or warming or even noticeable. It tells you only how fast the particles are moving. To know how much warmth will actually reach you, you must also know how many particles there are. And out in space, the answer is almost always the same. There are very few. And so the great rule of warmth in space is that almost everywhere, no matter how fast the scattered particles may be moving, there are far too few of them to deliver any warmth worth feeling, and an object placed among them will cool rather than warm. The thinness wins, nearly everywhere, over the speed. Consider our own star, and a place on it that surprises nearly everyone who first hears of it. The visible surface of the sun, the bright face we see, burns at around 10,000 degrees. But above that surface lies the sun's outer atmosphere, a faint crown of glowing gas that becomes visible only during a total eclipse. That crown is not cooler than the surface beneath it, as you might expect of something farther out. It is far hotter. It reaches 1 million degrees, and in places a few million, hundreds of times hotter than the surface it surrounds. And yet, that scorching crown holds very little heat. It is so thin, so close to an empty vacuum, that a spacecraft can pass through it without being destroyed by its temperature, because so few of those blistering particles ever actually strike the craft. This is the picture to carry forward. Out in space, you can have a temperature that is technically very high and a heat that is almost nothing, all at once, simply because the particles are spread so thin. The gas drifting between the stars can be measured at thousands of degrees, and still an object adrift in it would freeze because there are so few particles to deliver any warmth. The thermometer would not read what your intuition expects, because your intuition was built in the thick, crowded air of Earth, where temperature and heat travel together. In the thin emptiness of space, they part ways. It is worth dwelling on the space between the stars itself, because it shows this idea at its strangest. That space is not perfectly empty. It holds a thin drift of gas, mostly the lightest of all atoms, scattered so sparsely that a handful of them might occupy a space where, in the air around you, there would be countless billions. In some regions, this thin gas is genuinely hot by the measure of temperature, its few atoms moving very fast, heated by the light of nearby stars or the shock waves of old explosions. A thermometer, able to read only the speed of those atoms, might call that region thousands or even millions of degrees. And yet a traveler passing through it would feel nothing but the cold, because there are so few atoms that almost none would ever touch them. The warmth is real, by definition, and useless, by quantity. This is one of the quiet surprises waiting for anyone who looks closely at space. The same emptiness can be called both scorching and frozen, depending on which question you ask. Ask how fast the few particles move, and the answer may be enormous. Ask how much heat would actually reach an object placed there, and the answer is almost none. Both answers describe the same thin gas. They only measure different things. Temperature asks about speed. Heat asks about how much energy actually arrives. And in the thin reaches of space, those two questions, which march together in the thick air of Earth, wander far apart. There is a homely version of this we have all felt without naming it. Open the door of a hot oven, and the air that rushes out, though it is hundreds of degrees, does not burn you, because air is thin and carries little heat. But brush a finger against the metal rack at the same temperature, and you are burned at once, because the dense metal holds far more heat and delivers it instantly. Same temperature, the air, and the rack, and wildly different danger, purely because one is thin and one is dense. The air of space is thinner still than the air of any oven, thinner than the finest laboratory vacuum, and so it can hold a furious temperature and deliver, to anything passing through, very nearly nothing at all. So when we say space is cold, we are saying something careful. We do not mean that every particle out there is slow. Some are fast, even furious. We mean that an object placed in that emptiness, far from any star, will lose far more warmth than it gains, and will settle toward the cold, because the sparse particles around it can give it almost nothing. What a thing settles to in space does not depend on the temperature of a few stray particles passing by. It depends on a balance, the balance between the radiation it soaks up and the radiation it sheds. And to understand that balance, we have to look at the few ways heat can travel at all, and discover that in space, nearly all of them stop working. Part 4. The 3 roads heat can travel. Heat moves from one place to another in only 3 ways. Naming them plainly gives us the frame for everything that follows, because the whole reason space is cold turns on a simple fact that 2 of these 3 roads close completely in the emptiness and only one remains open. Once that is clear, the cold of space stops being a mystery and becomes almost inevitable. The first road is conduction. Conduction is heat passing directly from particle to particle by touch. Hold a metal spoon in a cup of hot soup, and after a moment the handle grows warm, even though the handle never touched the liquid. The fast-moving particles at the hot end of the spoon jostle their neighbors, which jostle theirs, passing the motion steadily along the metal until it reaches your hand. Conduction needs a chain of particles in contact, each able to nudge the next. It is how warmth spreads through anything solid, and it is why a cold floor pulls the heat from a bare foot, drawing your warmth away by simple contact. The second road is convection. Convection is heat carried by a moving fluid, a liquid or a gas, that flows and takes its warmth along with it. Warm air rises and cool air sinks, and the slow circulation carries heat around a room. Water at the bottom of a heated pot warms, rises, and is replaced by cooler water falling to take its place until the whole pot is stirred and warmed. Convection is why a breeze feels cool against the skin, carrying warmth away, and why the weather of a whole planet can move heat from the warm middle toward the cold ends. It needs a fluid that can move, and it carries the heat bodily from one place to another. The third road is radiation. Radiation is heat traveling as light. Every warm object glows, shedding some of its energy as electromagnetic waves, and much of that glow is infrared, the invisible light we feel as warmth without seeing it. It is how the heat of a fire reaches your face across a room without warming the air in between. It is how the warmth of the sun crosses 93 million miles of empty space to fall on the skin of the earth. And here is the property that matters most for our story. Radiation needs no material at all to travel through. It crosses empty space as easily as it crosses a room. It is the one road that does not require particles to carry it. On our own world, all three of these roads work together at every moment, so smoothly that we never notice them as separate things. The warmth of a fire reaches across a room as radiation warms the air, which then rises and circulates as convection, carrying the heat to the far corners where it passes into the cool walls and floor by conduction. A pot on a stove takes heat by conduction from the burner, stirs it through the water by convection, and glows a little of it outward as radiation all the while. Warmth on Earth is never traveling by one road alone. It moves by all three at once, the three forever sharing the work, which is exactly why heat spreads so quickly and so evenly here, and why we almost never have to think about how it gets from place to place. The air and the water and the solid ground give warmth so many roads to travel that it can never be trapped for long. Now place all three roads in the emptiness of space and watch what happens. Conduction needs a chain of touching particles, and in the vacuum there are almost none, so conduction nearly stops. Convection needs a flowing fluid, and in the vacuum there is no fluid to flow, so convection stops completely. Two of the three roads simply close. Only radiation remains. And so the warmth of a star can travel outward in only one way, as light, and a warm object in space can lose its heat in only one way, by glowing it away. Every part of the puzzle from here forward follows from this single fact. It is worth lingering on each of these roads a little longer, because the difference between them is the difference between a warm world and a frozen one. Conduction is the most intimate of the three, the passing of warmth by direct contact, and it is everywhere in daily life. It is the warmth that creeps up the handle of a pan, the chill that seeps into your hands from a cold railing, the heat that flows from your body into a cool sheet until the sheet grows warm beneath you. Conduction is fast and effective wherever particles are packed close enough to touch, which is why metals, dense and tightly knit, carry heat so readily and why they feel cold to the touch, even at room temperature, because they pull your warmth away so quickly. Convection is the great mover of heat across the surface of our world, and it depends entirely on having a fluid free to flow. It is the rising of warm air from a candle, the circulation that carries heat from a radiator to fill a room, the slow overturning of the oceans and the restless movement of the air that together carry warmth from the warm middle of the planet toward its cold ends. Every wind is convection at work, every ocean current, every rising plume of warm air over a sunlit field. It is powerful precisely because the fluid carries its heat bodily from place to place, the way a river carries everything floating on it downstream. But it cannot work without the river. Take away the fluid, and there is nothing to do the carrying. Radiation is the quietest and most patient of the three, and the only one that needs nothing at all. Every object that has any warmth glows, sending its energy out as light, most of it in the invisible infrared we feel but cannot see. You are glowing now, softly, in infrared light, and so is everything around you, and so is the ground, and the sky, and the snow on a winter field. Warmer things glow more strongly, and cooler things more faintly, but everything glows, always, shedding a little of its warmth into the space around it, as light. This glowing needs no air, no contact, no fluid. It crosses an empty room, and an empty universe with equal ease. It is the warmth of the fire on your face and the warmth of the sun on your skin, and it is the one and only way that heat can ever cross the emptiness of space. This is why our ordinary intuitions about heat fail so badly once we leave the air behind. On Earth, a warm object in a cold room loses heat quickly because the surrounding air carries it away by convection and conduction at every moment. Take away the air, and those fast roads vanish. The object can now lose heat only by the slow road of radiation, glowing its warmth into the dark, and it can gain heat only the same way, by absorbing whatever light happens to fall on it. The entire thermal life of everything in space, every star and world and drifting spacecraft, runs along this single, narrow channel. And the next thing to understand is how that one open road both saves warmth and lets it slip away. Part 5. The vacuum that keeps and loses. There is a small paradox tucked inside the larger one, and it is worth pausing on because it is satisfying once it clicks into place. The vacuum of space is at the same time the finest insulator that exists, and a place where an unprotected thing will surely freeze. Both are true, and remarkably, they are true for exactly the same reason. Because a vacuum has no particles to conduct heat and no fluid to convect it, it blocks 2 of the 3 roads heat can take. Warmth cannot cross an empty gap by touch, because there is nothing to touch. It cannot cross by flow, because there is nothing to flow. This is precisely how a vacuum flask, the kind that keeps coffee hot through a long morning, does its quiet work. Between its inner and outer walls lies a thin gap with the air pumped out, a small sleeve of vacuum. Heat cannot conduct or convect across that empty gap, and so the warmth inside is held, hour after hour. The same flask keeps a cold drink cold by the same trick, refusing to let outside warmth cross the gap inward. Empty space is the best insulating blanket there is, and we have learned to wrap a little of it around our drinks. And yet, things in space still cool. They cool because the one road a vacuum cannot block is radiation. A warm object surrounded by emptiness cannot lose its heat by touch or by flow, but it can still glow that heat away as infrared light, steadily, into the dark around it. And with nothing nearby glowing back at it with equal strength, it loses more than it gains, and slowly cools. The vacuum flask knows this too, which is why its inner surface is silvered like a mirror, to catch that radiated warmth and reflect it back inside before it can escape. The mirror is what makes the flask truly work. Space, of course, has no mirror. There is nothing out there in the dark to reflect a warm object's glow back to it. And so the warmth simply leaves, radiated outward into the emptiness, never returning. This is the resolution of the small paradox. The vacuum keeps warmth from crossing it by the 2 fast roads, and so it insulates beautifully. But it cannot stop the warmth from leaving by the slow road of radiation, and so a thing inside it, with nothing to reflect its glow back, will still grow cold in the end. Space insulates against the cold outside and lets the warmth inside escape both at once, and there is no contradiction in it. It only does what an empty gap does, which is to close the roads of touch and flow while leaving the road of light wide open. The same principle, turned to our advantage, is what lets spacecraft survive at all. The thin shells that wrap a satellite or a probe are often built from many fine layers with a near vacuum held between them, sheet upon sheet of thin reflective material, each one blocking the slow road of radiation a little more. It is the thermos flask written across a whole machine, vacuum to close the roads of touch and flow, mirrored surfaces to turn the radiation back. With such a wrapping, A craft can hold its warmth through the long cold of the shadowed hours, or hold off the fierce heat of direct sunlight, keeping its delicate insides at a steady, survivable temperature, while the surfaces outside swing between extremes. The cold of space is managed not by fighting it with warmth, but by closing the roads along which warmth would otherwise escape. And the same understanding explains a thing that puzzles many people when they first hear it, which is that the cold of space, for all its severity, is not actually very good at chilling things quickly. On Earth, to chill something fast, we put it in cold water or a cold wind, letting conduction and convection pull the heat away in a rush. Space offers neither. It can take heat only by the slow road of radiation, and so it draws warmth out far more gently than a cold bath or a winter gale. A warm object in space cools surely and steadily, but it cools at the unhurried pace that radiation alone allows. The emptiness is brutally cold and oddly patient at once, a cold that always wins in the end but never hurries to do it. There is a plain demonstration of all this that anyone can picture. Two travelers in space, one wrapped in a layered, mirrored blanket, and one bare, set side by side, far from any star, will meet very different fates. The bare traveler glows its warmth straight out into the dark and cools steadily toward the cold of space. The wrapped traveler, its warmth caught and turned back by the mirrored layers with vacuum between them, holds its heat far longer, cooling so slowly that it stays warm long after the other has chilled. Nothing different is happening to the two of them. The same dark surrounds them both, asking nothing, taking warmth only by the one slow road of radiation. The only difference is that one has closed that road as far as it can be closed, and the other has left it open. The cold did not choose between them. They chose, by how they were wrapped, how quickly they would give their warmth away. So the vacuum holds two truths together without strain. It is the finest insulation there is, closing two of the three roads heat can travel and slowing the third. And it is a place where warmth, given long enough, will always drain away, because the one road it cannot close is the road of light, and there is nothing out in the dark to glow that warmth back. A thing in space keeps its heat far longer than it would on Earth, and loses it just as surely in the end. Both at once. The same emptiness doing both. There is something quietly restful in the picture once it is seen clearly. A warm thing adrift in space is not being chilled by anything at all. Nothing is reaching in. It is simply releasing its own warmth, gently, into a darkness that asks nothing of it and gives nothing back, settling over time toward the settled stillness of the surrounding cold. The losing of heat is not violent. It is a slow letting go, a warmth glowing outward into the dark until what remains comes to rest. And that resting point, the temperature a thing finally settles toward when it has given all the warmth it can, is the next piece of the answer. But before we can reach it, we have to follow the warmth of a star outward and watch how, even as light, it thins almost to nothing along the way. Part 6. How the light thins. If radiation is the only road open to a star's warmth, then the next question is what becomes of that warmth as it travels. And the answer is that it spreads out, and as it spreads, it thins, following one of the simplest and most far-reaching rules in all of nature. The rule has a plain name. It is called the inverse square law, and once you see it at work, you see it everywhere. Light leaves a star in every direction at once. It does not travel as a narrow beam, but as an expanding sphere, a growing shell of radiation rushing outward into the dark on all sides. Think of that shell swelling outward, larger and larger, like a bubble with no skin. The total energy in the shell stays the same as it grows, but the shell itself keeps getting bigger, so that same energy must spread across an ever larger surface. And here is the part that matters. The surface of a sphere grows with the square of its radius. Double the distance from the star, and the shell has 4 times the surface to cover. Triple the distance, and it has 9 times. The energy is not lost, but it is spread thinner and thinner across a surface that keeps outrunning it. What this means for warmth is direct. Move twice as far from a star, and the light falling on any given patch drops to 1/4 of what it was. Move 10 times as far, and it drops to 1/100th. Move 1,000 times farther, and it drops to 1,000,000th. The warmth does not fade gently or evenly. It falls away steeply, faster than distance alone, because the light is forever spreading across more and more space. A little way out from a star, the warmth is already much weaker. Far out in the dark between the stars, it is a feeble glow, a trickle too faint to warm anything to more than a few degrees above the absolute cold. We can watch this happen across our own family of worlds. Close to the sun, the light is concentrated and fierce, strong enough to scorch a surface and boil away any water. A little farther out, at the distance of our own world, it is gentle and life-giving, just enough to keep oceans liquid and air mild. Farther still, the warmth thins quickly. By the distance of the outer worlds, the sun is only a bright point in the sky, and its light has spread so thin that those worlds are frozen hundreds of degrees below anything we would call cold. The same star, the same fire, warming one world and abandoning another simply because the light has had farther to spread before it arrives. This same thinning of light explains something we look at every night without wondering why, which is that the sky between the stars is dark at all. The universe holds a staggering number of stars, more than anyone can truly picture, and you might think that with so many fires burning, the whole sky would blaze with their combined light. But it does not. The sky between the stars is black because the light of those countless distant fires, spread across the enormous distances between them, arrives so faint and so thinned that it cannot light the dark. Each far star is a pinprick, and the spaces between the pinpricks receive almost nothing, because every star's light has been fanned out across such an immense reach of space before it ever arrives. The darkness of the night sky is the inverse square law made visible, the thinning of starlight written across the whole of the heavens. And what is true of the light is true of the warmth it carries, for they are the same thing. If you could add up all the starlight crossing any patch of empty space far from any single star, all the light of all the galaxies arriving from every direction at once, it would still amount to almost nothing, a warmth far too faint to feel, far too weak to lift the cold, even a little above the floor the ancient background sets. The universe is full of stars, and still its spaces are cold and dark, because the fires are tiny and the distances between them are beyond all ordinary measure. The night is not dark for want of fire. It is dark because the fire is so very far away, and its light, by the time it crosses to us, has almost nothing left to give. And the stars are not packed close together. They are scattered across distances so great that the light between them spreads almost beyond measure. By the time the light of one star has crossed the immense gulf to the next, it has thinned to a whisper. This is why the night between the stars is dark and cold, even though it is filled with starlight. The light is there, crossing the emptiness in every direction, but it is spread so impossibly thin that it carries almost no warmth at all. The galaxy is full of fire, and still it is cold, because the fire is gathered into tiny points and the dark between them is enormous. You can watch the same law at work with any single light on a dark night. Stand close to a lamp, and it is bright enough to read by. Step back a few paces, and the page grows dim. Step back across a field, and the lamp shrinks to a small glow that lights nothing at all, though it is burning exactly as brightly as before. The lamp has not dimmed. The light has only spread, fanning out across more and more space, until by the far side of the field each patch of ground receives only the faintest trace of what fell on the page up close. Warmth behaves in exactly the same way as the brightness, because warmth, across the emptiness, travels as light. To move away from a fire is to let its warmth fan out and thin before it reaches you. The numbers across our own family of worlds make the steepness plain. Our world receives a certain warmth from the sun, enough to keep it mild and living. The world half again as far out receives less than half as much. The ringed world far beyond receives only about 1/100th of the sunlight we enjoy. And the dim outer worlds, far out in the cold, receive only 1,000th or less. A sunlight so weakened that noon there would seem to us like dim twilight. The sun is the same sun for all of them, unchanged, burning steadily at the center. Only the distance differs, and the distance is enough to turn a warm world into a frozen one, simply by giving the light more room to spread before it lands. And here is the part that matters most for the question we are chasing. The warmth that fails to reach the outer worlds is not destroyed along the way. It is not used up or worn out. It is simply spread across the enormous sphere of space surrounding the sun, falling on no one, crossing the emptiness in every direction at once. The same total warmth leaves the sun whether anyone is there to feel it or not. It is only that the warmth is shared across a sphere so large that any single patch of it receives almost nothing. The heat has gone exactly where the law says it must go, outward and thinner, forever. Here, already, we have most of the answer to where the heat goes. It is not destroyed. It is diluted. The same energy that would scorch a world close to a star becomes, light years away, a glow too faint to feel against the skin. Picture campfires scattered across a whole continent on a clear night. Stand beside one, and you are warm. But the night itself, all the dark miles stretching between the fires, stays cold, because the warmth of each fire fades to nothing, only a short way out from its flames. And the thinning never stops, no matter how far the light travels. There is no distance at which the spreading pauses, no shell at which the warmth gathers itself again. The light fans outward forever, growing fainter forever, so that a star bright enough to warm a nearby world becomes, far enough away, a point too dim to find without a telescope, and farther still, a warmth too faint for any instrument to measure against the cold. The fire does not go out. It only recedes, spreading its light across ever more space, until its warmth is diluted past all noticing. This is the quiet fate of every star's heat, and the reason the immense reaches between the stars stay cold, while the stars themselves blaze on. The galaxy is built like that. Warm in tiny scattered pockets. Cold across almost all the immense dark in between. The heat has gone nowhere. It could not go. It has only spread until there is too little of it in any one place to matter. Part 7. The slow cooling. With these pieces in hand, we can now follow exactly what happens to a warm object, left alone in the dark, far from any star. The process has a name as plain as the others. It is called radiative cooling, and it is the quiet engine behind everything else we will see tonight. Every object warmer than its surroundings glows, shedding energy as light. The warmer it is, the more strongly it glows, and most of that glow pours out as infrared, the invisible warmth we feel from a banked fire or a radiator across a room. Out in space, this glowing is the only way an object can lose its heat, and absorbing the light that falls on it is the only way it can gain any. Its fate hangs entirely on the balance of the two. If it glows away more than it takes in, it cools. If it soaks up more than it sheds, it warms. And when the two come exactly into balance, it holds steady, resting at what we call its equilibrium temperature, neither warming nor cooling any further. Now carry an object far out into the dark, away from every star. Almost no light reaches it there. It glows its warmth steadily outward into the surrounding emptiness and receives almost nothing back in return. The balance tips entirely toward loss. So it cools and goes on cooling, shedding its warmth into a dark that gives nothing back, sliding downward toward the coldest temperature its surroundings allow. There is no comfortable floor partway down where it stops. There is no chill that is merely brisk. The cooling continues all the way down toward a temperature only a few degrees above the absolute bottom, the coldest the universe permits. The speed of this cooling depends on how warm the object is and how much surface it has to glow from. A small, warm thing with a wide surface sheds its heat faster. A large, cool thing sheds it slowly. But the direction never changes. It is always downward, always toward the temperature of the surrounding dark. A human body, a spacecraft, a wandering rock far from the sun, each one left to itself will slowly release its warmth and settle toward the cold. Not in an instant, but steadily, like a single coal carried out into a winter night and set down on the snow, glowing its heat away into the dark until nothing warm is left in it. There is a quiet rule hidden inside this glowing, worth naming softly, because it shapes how everything in space cools. The hotter a thing is, the far more fiercely it glows. The relationship is steep, so that a very hot object sheds its warmth in a torrent, while a cold object releases only a trickle. This means that cooling is fast at first, while a thing is still warm, and then slows and slows as the thing grows colder, the glow fading along with the warmth that feeds it. A hot ember thrown into the dark loses its heat quickly at the start, glowing brightly as it goes, and then more and more slowly as it dims, taking a long, lingering time to shed the last of its warmth. Everything in space cools this way, in a rush that gradually becomes a crawl, approaching the cold of its surroundings ever more slowly the closer it comes. We can watch a gentle version of this on our own world, on any clear and windless night. The ground, having soaked up warmth from the sun all day, begins to glow that warmth away into the sky after dark, radiating it upward as infrared light. On a cloudy night, the clouds catch much of that glow and return it, and the ground stays mild. But on a clear night, the warmth escapes straight up into the open sky and is gone, and the ground cools quickly, sometimes enough for frost to form on the grass, even when the air never quite reached freezing. That frost is a small print of the cold of space, left on a lawn. It forms because the ground found, through the clear air, a direct road to radiate its warmth into the cold dark above, the same road every object in space is always traveling. Now take away even the thin protection of the air, and imagine a world with no sun at all, a wanderer drifting alone in the dark between the stars. Such a world would glow its warmth away into the emptiness and receive almost nothing back, and its surface would cool toward the great cold, settling at last only a little above the temperature of the dark itself. Any air it carried would freeze and fall as snow. Any ocean would harden to ice from the top down. The world would not die in fire, but in a long, slow surrender of warmth, glowing its heat patiently into the night until almost none was left, holding only whatever faint warmth still rose from far within its own rock. This is the fate of warmth left alone in space. Not a sudden freezing, but a long fading, a steady giving away of heat to a dark that never gives it back. This last image is worth correcting a common idea, because the truth is gentler than the stories. People often imagine that to enter the vacuum of space is to freeze at once, in a single violent instant. It is not so. Cooling by radiation alone is slow, far slower than the cooling we know on Earth, precisely because the fast roads of touch and flow are closed. Radiation is the only escape route for the warmth, and it carries heat away only gradually. An unprotected body in space would lose its warmth over a span of hours, cooling steadily rather than flashing to ice. The danger of the vacuum is real, but the freezing is not sudden. It is a long, quiet letting go of warmth, more like a fading than a shock. It helps to put a feeling of time to this, because the slowness is part of the gentleness. A warm body carried into space would not flash to ice in a moment, as the old films would have it. It would cool over a span of hours, the warmth glowing slowly outward, the chill creeping inward by degrees, far more gradually than the same body would cool if plunged into cold water on Earth, where the water carries the heat away in a rush. The vacuum, having only the slow road of radiation to draw heat by, is a patient thief rather than a sudden one. It takes everything in the end, but it takes it gently, and there is something almost merciful in that slowness, a cold that does not pounce but only waits. Larger things cool slower still. A whole world, with its enormous store of warmth and its great reserves of heat held far within its rock, can hold its temperature for a very long time, even with no star to warm it, glowing its heat away so slowly that ages pass before it truly grows cold. A small stone cools in hours, a world over ages, but the direction is always the same, always downward, always toward the temperature of the surrounding dark. The only question is how long the warmth takes to leave, and that depends only on how much warmth there is to lose and how slowly the glowing carries it away. Given enough time, everything left alone in the dark arrives at the same cold. So the cold of space is not something that strikes. It is something a warm thing drifts toward, slowly, on its own, once it is left in the dark, with nothing to keep it warm. And that raises the question we have been circling toward from the beginning. If everything out there is sliding down toward the temperature of its surroundings, then what is that temperature? What is the cold that the dark finally settles onto? The answer is not the perfect, absolute zero you might expect. It is a few degrees above it, held there by something faint and ancient and quietly astonishing, and that is where we turn next. Part 8. The warmth that never quite leaves. If a warm object in the dark cools toward the temperature of its surroundings, then everything depends on what that surrounding temperature is. And here we arrive at one of the most beautiful facts in all of science, a fact that turns the cold of space from a simple emptiness into something with a history. Empty space, far from every star, is not at the absolute bottom of cold. It rests a little above it, at about 2.5 to 3 degrees above the lowest temperature there is. And the reason it does not fall the rest of the way is a warmth that has been traveling toward us since the beginning of the universe. Space is filled, everywhere and in every direction, with a faint glow of light left over from the birth of the cosmos. Long ago, the entire universe was unimaginably hot and dense, an ocean of blazing radiation with no empty dark in it at all. Then it began to expand, and it has been expanding ever since. As space itself grew, The light within it was stretched along with it, its waves drawn out longer and longer. And longer waves of light mean cooler light. What was once a fireball filling everything has, over the long ages, been stretched and cooled into a whisper of faint microwave light, almost unimaginably weak, but still present in every part of space. This relic glow has a name. It is called the cosmic microwave background, and it bathes everything in the universe at just under 3 degrees above the absolute cold. This is the true temperature of empty space, far from any star. It is the floor that radiative cooling settles onto. An object out in the dark cannot cool below it by glowing into the background, because the background is glowing faintly back in every direction, holding the object at that few degree warmth. The cold of the space between the galaxies is not perfect nothingness. It is the cooled down, stretched out, barely there warmth of the universe's very first light, still arriving, still glowing, after all this time. It is worth walking slowly through what this ancient light actually is, because it changes the whole feeling of the cold. In the beginning, the universe was not only hot, but opaque, so dense and so bright that light could not travel freely through it at all, forever caught and scattered among the crowded particles. Then, as the universe expanded and cooled, a moment came when it thinned and calmed enough for light to slip free and travel in straight lines for the first time. That released light has been crossing space ever since, for the whole long age of the universe, never stopping, stretching longer and cooler with every passing era as space itself has grown. The faint glow that fills the sky today is that very light, the oldest light there is, set free when the universe first became clear. It comes from every direction at once, evenly, with no source you could point to, because it was not made by any star or any object. It was made by the whole universe at once, in its first clear moment, and so it fills the whole universe still, a soft and uniform warmth present in every cubic inch of space, in the room around you, as much as in the dark between the galaxies. When it was first noticed, it appeared as a faint hiss that could not be explained, a whisper of warmth coming from everywhere in the sky at the same time, impossible to aim at or escape. It turned out to be the light of the beginning, grown cold, still arriving. We are, in a quiet sense, always sitting inside the last embers of the universe's first fire. And this is why the cold of space has the exact value it does, just under 3 degrees above the absolute bottom, rather than the perfect zero you might expect of true emptiness. That number is not arbitrary. It is the present temperature of the universe's first light, after all its ages of stretching and cooling. Long ago that same glow was warm, then merely mild, and it has cooled steadily as the universe has grown, and it will go on cooling, slowly, for as long as the expansion continues. The cold of space is not a fixed floor set down once. It is a fading warmth, still very gradually falling, the long afterglow of the beginning of everything, cooling toward a zero it will approach forever and never quite reach. There is a quiet wonder in this worth sitting with. The coldest, darkest places between the galaxies, the emptiest reaches of all, are not truly empty and not truly without warmth. They are still faintly lit by the light of the universe's beginning, a warmth almost gone, but not quite, holding everything just above the absolute zero it would otherwise fall to. The whole sky, in every direction, is still very softly glowing from a fire that burned out long ago. We cannot see it with our eyes, but it is there, the oldest light there is, keeping the cold of space from ever becoming complete. And this leads to a gentle question. Why does space not simply reach the true bottom, the absolute zero we hear named so often? Absolute zero is the temperature at which the motion of particles falls to its quietest possible state, the true floor, where almost nothing moves at all. Nature never quite reaches it. In the dark between the stars, the relic glow of the early universe keeps everything those few degrees above it. Closer to stars, scattered starlight keeps things warmer still. And even in principle, the deepest laws of physics forbid anything from being chilled all the way to the absolute bottom, because to remove the very last trace of motion would take an impossible, endless effort. Space is colder than anything on the surface of the Earth, colder than the coldest winter that has ever been. But it is held forever just shy of the true zero, by the faint, universal warmth of that ancient background, the last fading light of the beginning of all things. So the cold of the open dark has a number, and a story behind the number. It is a few degrees above absolute zero, and it is held there by the oldest warmth in existence. But there are places, both made by nature and made by our own hands, that manage to dip below even that ancient floor. And those places have something to teach us too, about what cold really is and how it comes to be. Part 9. The coldest places of all. If the ancient background glow holds the dark between the stars at a few degrees above the absolute cold, it might seem that nothing could ever be colder than that. And yet there are places, some shaped by nature and some by our own careful hands, that fall below even that universal floor. Each of them reveals one more way that cold is made, and together they round out our understanding of how the universe grows so cold in the first place. Far out in the galaxy there is a small, dying star, casting off its outer layers into space as it nears the end of its long life. Around it has formed a faint cloud of gas, shaped a little like an hourglass, expanding outward into the dark. That expanding cloud is the coldest natural place ever measured anywhere, colder even than the background glow of the universe itself, only about 1 degree above the absolute bottom. And it is cold for a reason worth pausing on, because it shows us cold being actively created rather than simply settled into. The gas is rushing outward very fast, and a gas that expands quickly cools itself as it spreads. You have felt a small version of this. The air rushing out of an aerosol can grow cold as it escapes, chilling the nozzle against your fingers. On a far grander and slower scale, this dying star's outflowing breath has chilled itself below the temperature of the universe around it, pouring a pocket of cold out into the dark. Cold does not always require the distances between the stars, though. Sometimes it requires only shadow and stillness and time. At the poles of our own moon, so close that we have walked nearby, there are crater floors where sunlight has never once fallen. They are pits angled so steeply and a star so low on their horizon that for billions of years no ray of light has ever reached the bottom of them. These permanently shadowed places, never warmed and able only to glow their own faint heat away, are among the coldest spots in the entire solar system, colder than the surface of the most distant planet. They are so cold that they act as traps. Water, ice, and other frozen materials that drifted in long ago have settled there and never had the warmth to leave, held in the dark for the age of the solar system. Only a few miles away, in the sunlight, the ground can grow hot enough to burn. The two extremes sit side by side, with nothing between them but a line of shadow. The cold of expanding gas shapes more of the universe than that single dying star, too. Across the galaxy drift enormous clouds of gas and dust, and the quietest and densest of them are among the coldest large places in nature, only a little above the temperature of the universe's background glow. In their cold and dark interiors, shielded from the warmth of nearby stars, the gas grows so still and so chilled that it can begin to draw together under its own faint pull, slowly gathering, slowly collapsing, until far within the cold a new star kindles and begins to shine. There is a gentle symmetry in this worth noting. The coldest clouds in the galaxy are the very nurseries where new warmth is born, and every star that burns began as a knot of gas, chilled almost to the temperature of the dark. Cold and fire are not opposites here, but stages of one slow turning, the cold gathering the gas, the gathering lighting the fire. This nearness of fire and cold on an airless world is worth holding clearly because it shows the whole story in miniature. With no air to carry warmth across the boundary, the line between blazing sunlight and brutal cold can be a single step wide. Stand with 1 foot in the sunlight and 1 in the shadow of a boulder, and the 2 feet would rest in different worlds, 1 scorched and 1 near the deepest cold, with no breeze, no air, nothing at all to soften the border between them. On Earth, the air blurs every such edge instantly, sharing the warmth around. In space, the edges stay sharp, and heat and cold lie down beside each other without ever mixing. The way that dying star chills itself is worth understanding, because it is the same trick that powers the cold of a winter morning's frost and the chill of a mountain wind, only carried to an extreme. When a gas expands, its particles spread apart, and as they spread, they slow, and slowing is cooling. The energy that was motion becomes the work of pushing outward into more space, and so the gas grows colder simply by growing larger. The breath that fogs cold on a winter day, the chill of air rushing from a valve, the cooling of the high, thin air where clouds form and snow is born, all of these are the same effect at gentle scale. The dying star, casting its outer layers outward at tremendous speed, is doing only this, expanding and cooling, but on a scale and at a pace that has carried a whole cloud of gas below the temperature of the universe around it. And the cold traps of airless worlds deserve a longer look because they hold something precious. On both the moon and the small scorched world closest to the sun, there are craters near the poles so positioned that their floors lie in permanent shadow, never once touched by sunlight, across the entire age of the solar system. With no light ever falling in, and only the slow glow of their own faint warmth leaking away, those crater floors have settled to among the coldest temperatures anywhere near us, far colder than the night side of any planet. And because they are so cold, they have become keepers. Water and other frozen materials that drifted in long ago, carried by comets and the slow rain of space, fell into those shadows and could never gather the warmth to leave again. So, in the permanent dark, only steps from sunlight fierce enough to melt lead, there are stores of ancient ice that have waited, frozen and undisturbed, since the worlds were young. The hottest and coldest places of a world, side by side, with a line of shadow between them. And then there is the coldest place of all, which is not in space at all. In quiet rooms on the warm surface of the Earth, people have learned to chill small clouds of atoms to within a tiny fraction of a single degree of the absolute bottom, colder than the dying star's breath, colder than the darkest crater, colder than anywhere known in all of nature. At those temperatures, matter begins to behave in strange and gentle new ways, the particles slowing so far towards stillness that they seem almost to merge into one calm, shared whole. There is a reason these laboratory colds, for all their care, can never quite reach the true bottom, and it is worth saying gently, because it tells us something about the nature of cold itself. To cool a thing is to remove its motion, and the colder it grows, the harder it becomes to coax out the last remaining traces of that motion, the way the last drops are always the hardest to pour from a vessel. Each step closer to the absolute bottom demands more effort than the step before, and the very final step, the removal of the last trace of all motion would demand an effort without end. And so absolute zero stands as a limit that can be approached forever and never quite touched. A floor that nature draws nearer and nearer to, but never reaches, neither in the coldest crater, nor the dying star's breath, nor the most patient laboratory on Earth. This means the cold of space, for all its severity, is not the perfect stillness of the absolute bottom. It is a cold held a few degrees above it by the ancient background glow, and even that faint glow is slowly fading as the ages pass. The universe is cooling, gently, toward a zero it will chase forever. There is no perfect cold anywhere, no place where all motion has truly ceased, only places that have come very close, and the dark between the stars is one of the closest of all. It rests near the bottom of everything, just above the floor that nothing can ever truly reach. These are the coldest places that have ever existed anywhere in the universe, as far as we know, and they sit not in the depths of space, but on the surface of a warm, living world. It is a quiet reminder of what cold truly is. Cold is not a place. It is a condition, the stilling of motion, and it can be reached anywhere the warmth is patiently coaxed away. Part 10.2 Temperatures at once. Nowhere is the strangeness of heat in space easier to feel than in the daily life of a spacecraft. Without air to even things out, an object in orbit lives at two temperatures at the same time, and the people who build such craft must work constantly to keep them from cooking on one side and freezing on the other. It is the whole paradox of this video made vivid in metal and shadow. On Earth, we never meet this strangeness, because the air around us is forever blending the warmth, carrying it from the sunlit side of any object to its shadowed side, smoothing away the difference before it can grow. A stone sitting in the afternoon sun is a little warmer on its lit face than its shaded one, but only a little, because the air keeps sharing the heat around. Remove the air, and that gentle sharing stops entirely. The sunlit face climbs, and climbs with nothing to carry its warmth away, while the shadowed face glows its heat into the dark and falls, and nothing crosses between them. The two faces, inches apart, drift to temperatures further apart than anything we ever feel on the ground. This is why an object in space does not really have a temperature in the way a thing on Earth does. It has many temperatures at once, a different one on every face, depending on whether that face looks toward a star or into the dark. There is no single, settled warmth shared across it, because there is no air to do the settling. And so the whole craft of keeping things alive and working in space becomes the craft of managing these separate temperatures, moving heat deliberately from the side that has too much to the side that has too little, doing by careful design what the air does for us, freely and unnoticed, every moment of our lives. Picture a spacecraft circling above a planet, half of it lit by direct sunlight and half of it turned away into shadow. The sunlit side soaks up the full strength of the star's radiation, and with no air to carry that warmth away, it climbs steeply, well past the boiling point of water, to more than 250 degrees. At the very same moment, the shadowed side faces only the dark. It glows its warmth outward and receives almost nothing back, and it falls to more than 200 degrees below zero. The same craft, in the same instant, holds a searing surface and a frozen one only a few feet apart, because there is no air between them to share the heat and split the difference. On Earth, the surrounding air would erase such a gap in seconds. In space, the two extremes simply sit beside one another, unmixed. This is why a large station carrying a crew cannot just float in sunlight and remain comfortable. Sunlight pours in from outside, and within, the bodies of the crew, and all the working electronics give off heat without pause. In a vacuum, that heat has nowhere to go on its own, because the fast roads of touch and flow are closed. The station would steadily warm and keep warming until it grew dangerously hot if it could not actively force the heat back out. So it carries great panels turned away from the sun toward the cold of empty space, and the only job of those panels is to glow the unwanted warmth away as infrared light. A vehicle in space must shed its heat the same slow way a warm rock does, by radiating it into the dark, and entire systems are designed around that single patient channel. The same truth shapes the suit a person wears to step outside. It is easy to assume such a suit is mainly a shield against the cold, but much of the time it is fighting the opposite battle. The body inside it is always producing heat, and on the sunlit side, the star is pouring more heat in. And in the vacuum, none of that warmth can escape on its own. So the suit circulates cool water against the skin to carry the heat away, and it radiates that warmth outward, balancing a person caught between a scorching sunlit side and a freezing shadowed one. The greater danger, often, is not freezing but overheating, because in the vacuum, the body's own warmth has nowhere to go unless the suit carries it off deliberately. This swing between extremes is not a single event, but a rhythm, repeated again and again. A craft circling close to a planet may pass from full sunlight into the planet's shadow and back again many times in a single day, and each time it does, its surfaces must heat and cool, expand and contract, swinging through hundreds of degrees in the span of a single orbit. Metals grow and shrink as they warm and cool, and a surface forced through that swing thousands upon thousands of times is under constant quiet strain, the materials worked back and forth like a wire bent again and again. Much of the careful work of building a spacecraft is the work of surviving this endless thermal tide, choosing materials that can bear it, and arranging the craft so that no part bakes or freezes past what it can endure. On worlds with long days, the same swing plays out far more slowly and reaches even further. On the Moon, a single day and night lasts about a month, and so each spot on its surface bakes in continuous sunlight for roughly 2 weeks, and then freezes in continuous darkness for 2 weeks more. The sunlit ground climbs to well above the boiling point of water, and the night ground falls to more than 250 degrees below zero, a swing of more than 400 degrees between noon and midnight at the very same spot. A machine left on that surface must endure both the long bake and the long freeze, with nothing but the slow road of radiation to shed its heat by day, and nothing to warm it through the endless cold of the 2-week night. Even the people who walk in space carry this balance with them in every moment. The gloves and boots of a suit, reaching toward sunlit metal or hanging in shadow, must guard against both burning and freezing at once. Heaters warm the fingers against the cold while cooling water carries away the heat of the body and the sun, all within the same small garment, because the wearer is always caught between the two extremes that have no air between them to split the difference. To step outside, into space, is to step into a place that has no single temperature to offer you, only fierce sunlight on one side and the cold dark on the other, and the constant quiet work of staying balanced in between. The lesson the spacecraft teaches is the lesson of the whole night, written plainly. In space there is no shared, surrounding warmth to settle into. The way a room settles to one even temperature that everything in it comes to share. There is only the radiation a thing receives and the radiation it gives off, sunlight on one face and the cold dark on the other, and the constant, careful work of staying balanced between them. A world, a station, a single drifting craft, each one hangs in that same balance, warmed only by the light that reaches it, and cooled by the dark it glows into, And that balance, scaled up to whole planets, explains one of the most familiar facts about our own solar system, which is where we turn next. Part 11. A temperature set by distance. Once we understand that everything in space hangs in a balance between the light it absorbs and the warmth it glows away, one of the most familiar facts about the solar system falls neatly into place. The worlds close to the sun are warm, and the worlds far from it are frozen. This is not because space itself somehow grows colder as you travel outward in any simple, even way. It is because the balance point shifts steadily as the sunlight thins with distance. Every world hangs in the same balance as any other object adrift in space. It absorbs the sunlight that falls upon it, and it glows its own warmth back into the surrounding dark, and it settles at exactly the temperature where the two come into balance, where the warmth arriving equals the warmth departing. Close to a star, where the light is concentrated and strong, that balance point is warm. Far from the star, where the light has thinned to a faint trickle by the spreading we traced earlier, the balance point is bitterly cold. The very same world, carried inward toward the sun, would warm. Carried outward into the dark, would freeze. Its temperature is not a fixed possession it carries with it. It is a setting, dialed up or down by nothing more than its distance from the fire. This idea of a balance point deserves to be felt rather than only stated, because it governs the temperature of nearly everything in the universe that is not itself a star. Every world, every moon, every drifting rock finds the temperature where the warmth it absorbs from the light falling on it exactly equals the warmth it glows back into the dark. Below that temperature, it absorbs more than it sheds and warms. Above it, it sheds more than it absorbs and cools. And so it settles, naturally and without effort, at the one temperature where the two are in balance, and holds there for as long as nothing changes. It is a kind of quiet equilibrium that everything in space falls into, each object resting at the temperature its distance and its surface together allow. Move an object closer to the star, and its balance point rises, because more light now falls on it, and it warms until it glows strongly enough to match the greater warmth arriving. Move it farther, and the balance point falls, the light thinning until the object can match it while barely warm at all. The temperature of a world is not a thing it was born with and carries forever. It is a setting it finds, again and again, wherever it happens to be, dialed entirely by the strength of the light it stands in. Carry a frozen outer world inward toward the fire, and it would slowly warm to mildness and then to scorching. Carry a warm inner world outward, and it would slowly freeze. Each would simply find the new balance, its new distance, allowed. Travel outward in the mind and watch the setting fall. In close to the sun, a world is bathed in fierce light and settles at scorching temperatures, hot enough on its sunlit face to melt soft metals, even with no air at all to hold the heat in. A little farther out lies the gentle middle distance, the narrow band where a world receives just enough warmth to balance at mild temperatures, where water can rest as a liquid on the surface and air can stay soft and breathable. This is the rare and quiet zone where our own world turns, neither scorched nor frozen, held at the temperature of life by nothing more dramatic than how far it sits from the star. Keep traveling outward and the warmth keeps thinning. By the distance of the outer worlds, the sun has shrunk to a bright point in a black sky, and its light arrives so weak and spreads so thin that those worlds settle at hundreds of degrees below zero. Their surfaces are frozen hard as stone. Their air, if they have any, has thinned to a trace or settled as frost across the ground, or is held only under crushing weight. Farther still, in the dark realm beyond the planets where small icy bodies drift, The sun is barely brighter than the other stars, and the cold approaches the great cold of open space. The fire is the same fire. It has simply had too far to spread before it arrives. There is a softening detail that makes this picture richer, and it explains why a world's air matters as much as its distance. A bare world, all rock and no atmosphere, simply settles at the balance point its distance sets, scorching on the sunlit face and frozen on the dark one, with nothing to carry warmth between them. But give a world a blanket of air, and the story changes. The air catches some of the warmth the surface tries to glow away, holding it close and returning part of it, so that the world settles a little warmer than its distance alone would allow. The air also flows, carrying heat around the world from the lit side to the dark one, softening the difference between day and night until the whole surface shares a gentler, more even warmth. This is why two worlds, at the very same distance from a star, can wear entirely different temperatures, one frozen and bare, the other mild and wrapped in cloud. The thicker the blanket of air, the more warmth it holds, and the more evenly it spreads, until on some worlds, the night side is scarcely cooler than the day. On a world with a thick enough atmosphere, the trapped warmth can build until the surface grows far hotter than its distance from the star would ever suggest, hot enough to glow, held in by an unbroken blanket of heavy air. Distance sets the starting point, but the air a world carries decides how much of that warmth it keeps and how kindly it shares it around. Our own world sits in the gentle middle of all this, at a distance that gives it mild sunlight, wrapped in just enough air to hold a little extra warmth and carry it evenly from the sunlit side to the shadowed one. It is this combination, the right distance and the soft blanket of air together, that keeps the whole surface within the narrow band where water stays liquid and life can hold on. Move the same world inward and the blanket would trap too much and it would bake. Move it outward and the thinning sunlight would let it freeze. The mildness we live inside is a balance so fine that it can feel almost unlikely, a quiet equilibrium between the fire of a distant star and the cold of the surrounding dark. This is the clearest reason there is no single temperature of space. Right beside a star, it is searing. A comfortable distance away, it is mild. Far out in the dark, it is deathly cold. The vacuum itself sets none of this. The distance to the nearest fire sets all of it, through the plain arithmetic of how much light arrives against how much warmth escapes. And so the cold of the empty dark and the warmth of a sunlit world are not two different laws at war with each other. They are the same single law, read at two different distances from a star. The same rule that warms a world close in, abandons a world far out, and there is no contradiction between them, only distance, doing quietly what distance does. Part 12. The Ladder of the Sun. To feel the paradox in full, it helps to climb outward through the layers of our own star and watch its warmth thin away into the dark, a single slow journey from the hottest place we know of, anywhere nearby, to the cold that finally swallows it. The sun is our nearest fire, and following its heat from the center to the edge, gathers nearly every idea of this night into one continuous climb. At the very center of the sun, under the crushing weight of all the layers above, the temperature reaches around 27 million degrees. This is the furnace. Here the sun does what stars do, pressing the nuclei of the lightest atoms together so forcefully that they merge into heavier ones, releasing the energy that powers the star and, in time, lights our sky. Almost all the warmth in the entire solar system is born here, in this hidden core, in a fire so concentrated that a piece of it, the size of a pinhead, would be lethal from across a room. This is as hot as anything gets in our corner of the universe, and it is buried at the center of the nearest star, pouring out energy every second without pause. The fire at that center is of a particular and patient kind, worth a quiet word, because it is the source of nearly all the warmth we have spoken of tonight. The sun does not burn the way a fire burns. It fuses, pressing the lightest atoms together under unimaginable pressure until they merge into slightly heavier ones, and each merging releases a small portion of energy. So gentle is this process, spread across so enormous a body that any small piece of the sun's core actually gives off rather little heat for its size, less than a warm living body of the same weight. It is only because the sun is so enormous, with so countless many of these mergings happening at once, that the total warmth becomes the flood of light that fills our sky. The star is not a quick and violent fire, but a slow and steady one, which is exactly why it can burn so evenly for billions of years. And it will go on burning for billions more, this patient furnace, far longer than it has already lived. The warmth it pours out today, the warmth that lights our world and stirs our weather and falls gently on your face on a clear afternoon, is the same warmth it has been pouring out for ages and will keep pouring out for ages yet to come. There is a settled steadiness in that thought. The fire at the center of our sky is old and will be long-lived, a furnace that has kept its slow and even pace since long before there was anyone to feel its warmth, and will keep it long after this night is forgotten. The energy born in that core does not rush straight out into space. It begins an extraordinarily slow climb through the dense layers above it, absorbed and given off again countless times, nudged this way and that, taking an astonishingly long time to work its way upward, far longer than the few minutes the light will later take to cross all the space between the sun and the earth. And as it climbs, it cools. By the time the energy reaches the visible surface of the sun, the temperature has fallen from millions of degrees to around 10,000. This glowing surface is the bright face we see, the layer from which sunlight finally breaks free and streams out into space in every direction at the speed of light. Then something strange happens, and it remains one of the genuine unsolved puzzles about our star. Above the visible surface, instead of continuing to cool with height, as you might expect, the temperature climbs again, and climbs steeply. The sun's outer atmosphere, the faint crown that appears during a total eclipse, is hundreds of times hotter than the surface beneath it, soaring back up into the millions of degrees. How a cooler surface can be wrapped in a far hotter crown is not fully understood even now. It appears the sun's restless, tangled magnetic fields carry energy upward and release it there, but the details remain open. We can hold this lightly, as a piece of honest wonder. Even the star closest to us, the one we have studied longest and know best, still keeps a few of its quiet secrets. It is worth pausing on the slowness of that inner climb, because it holds a quiet marvel. The light that warms your face on a sunny afternoon began as energy released in the sun's core, and that energy may have spent an immense span of time, far longer than all of recorded history, working its way out from the center to the surface, absorbed and released again, over and over by the crowded matter it had to cross. Only in the last stretch, once it broke free of the surface, did it cross the open space to the earth in about 8 minutes. So the sunlight on your skin is, in a sense, ancient at its source and swift only at its end, energy born long ago in the center of a star and set free into space just minutes before it found you. The surface it finally escapes from is not smooth or still, though from far away, it looks like a calm disk of light. Up close, it is a roiling, granular sea, its whole face covered in countless bright cells of hot gas rising from below, each one larger than a country, surrounded by darker lanes where cooler gas sinks back down. It is convection made visible, the same overturning that stirs a heated pot, carrying heat up from within to the surface, where it can finally glow away into space. Across this restless surface drift cooler, darker patches where the sun's magnetic fields press up through, and great arcs and loops of glowing gas rise and fall, the outward signs of the star's restless inner life. All of it is the machinery by which the furnace at the center delivers its warmth to the surface and releases it, at last, as the light that crosses the dark to us. And once that light leaves the surface, it travels outward in every direction into a system that grows colder and emptier with every mile, until the sun's warmth is spread so thin it can no longer hold back the cold of the stars. The thin wind of particles that streams from the corona carries on far past the most distant planets, blowing a great quiet bubble in the gas between the stars. And only at the far edge of that bubble, an immense distance out, does the sun's influence finally give way to the cold drift of the galaxy beyond. That edge is the true shore of the sun's domain, the place where the last of its warmth and its wind fade into the general dark, and everything past it belongs not to our star, but to the long, cold night between the stars. And here the ideas of this night fold together, because that scorching crown is the perfect picture of temperature, without much heat. It is millions of degrees, and yet so thin, so close to empty, that it holds very little warmth in total. From it, a steady stream of particles flows outward in all directions, a thin wind blown from the sun, carrying the star's influence far past the planets. But that wind thins as it goes, spreading and cooling, growing fainter with every mile, exactly as the light does. Far beyond the outermost worlds, it finally grows too weak to push back against the thin gas that drifts between the stars, and there, at the quiet edge of the sun's long reach, the warmth of our star fades at last into the general cold of the galaxy. Every bit of heat the sun has ever made ends the same way. Born in a furnace, carried slowly outward, spread thinner and thinner by distance, and released in the end into the dark between the stars. Part 13, where the heat finally goes. Now we can answer, directly and gently, the question written on the cover of this video. If the stars are forever pouring out heat, and have been for billions of years, where does all of it end up? The universe is not slowly growing warmer. The heat does not gather and pile up somewhere. So where does it go? We have gathered every thread we need, and we can follow it to its quiet end. It radiates outward as light, and it spreads. By the same rule we traced earlier, it thins as it travels, the same energy stretched across larger and larger shells of space until, far from its source, it has faded to a feeble glow. That is the first and largest part of the answer. The heat is diluted, spread so thin across such enormous distances that almost nowhere is there enough of it gathered in one place to warm anything. The fire is real, but it is poured out into so much dark that it thins to almost nothing nearly everywhere. Some of the light meets the scattered dust and gas that drift in the space between the stars. That thin material soaks up the light, warms very slightly, and then glows the energy out again at longer, cooler wavelengths, handing the warmth onward in a fainter and redder form. The heat is passed along, weakened at each step, drifting outward through the galaxy. And a great deal of the light simply streams onward into the immense spaces between the galaxies, crossing distances so great that it may travel for ages without ever falling on anything at all, carrying its small share of a star's warmth out into the dark with no end in sight. And then there is the grandest dilution of them all. The universe is expanding. Every region of space is slowly growing more distant from every other. the whole cosmos quietly stretching as the ages pass. As light crosses these enormous growing distances, it is stretched along with them, its waves drawn out longer, which means it loses energy and cools in exactly the way the universe's first light has been stretched and cooled into that faint background glow we spoke of. The heat of the stars, set loose into an expanding universe, is not only spread thinner across space, but stretched and cooled by the growing of space itself. The warmth is poured into a room that is forever getting larger, and so it can never fill the room, never gather, never warm the whole. There is a single quiet principle underneath all of this spreading, and it is one of the deepest patterns in all of nature. Energy, left to itself, always tends to spread out, to even itself across whatever space it is given, to move from where it is concentrated toward where it is thin. A warm cup, left in a cool room, never grows warmer while the room grows colder. Always the warmth flows outward from the cup into the room until the two are the same, and never the reverse. This one-way drift, from gathered toward spread out, from hot and cold toward evenly warm, is the direction that nearly everything in the universe quietly follows, given time. The heat of the stars obeys it as surely as the warmth of a cup, flowing always outward, always toward evenness, never gathering itself back. Carried to its far end, across spans of time so long they can barely be named, this points toward a universe that has shared its warmth out almost completely. Every star, long since burned down, every furnace gone cold, the energy that once blazed in concentrated points now spread so thin and so evenly that nothing anywhere is much warmer or much colder than anything else. It is a far-off and gentle ending, unimaginably distant, nothing to trouble any night of ours or any night for ages beyond counting. But it is the direction, the slow and patient drift of things, the universe easing always toward a single shared and even calm. The cold of space and the warmth of the stars are the two ends of that drift, caught in the middle of its long unwinding, and we live in the bright early part of it, while the fires still burn. So this is the answer, stated as plainly as it can be. The heat is never destroyed. Not one bit of it is lost. It is only spread thinner and thinner, diluted by distance, handed off to drifting dust, and stretched and cooled by the slow expansion of the universe, until it is everywhere at once and warm almost nowhere. That is where the heat goes. Not away, just thin. Spread out across so much space and stretched by the growing of space that it fades into the gentle, even, almost nothing warmth that fills the whole of the dark. There is a way of seeing the whole of it that ties these threads into one. At the beginning, the energy of the universe was gathered, concentrated, packed into a small and blazing space. Ever since, it has been spreading, pouring outward, gathering into stars and then streaming away from them, always moving from the concentrated toward the spread out, from the gathered toward the shared. A star is a brief, brilliant knot in that long unwinding, a place where energy is briefly drawn together and made to burn, before it is released again into the dark to continue its outward drift. Every star is a temporary gathering of warmth on its way to becoming part of the general cold. The drifting dust and gas between the stars play their quiet part in this spreading. When starlight falls on those thin clouds, they soak up its energy and glow it out again, but more softly, at the longer and cooler wavelengths of the infrared, light too red for the eye to see. Whole galaxies glow this way, in infrared, warmed faintly by all the starlight caught and re-released by their dust, shining softly in a light we can detect but never see. It is the warmth of countless stars, passed once through the dust and handed onward in a gentler form. One more step in the long journey of heat from the fierce and concentrated toward the faint and spread out. And the expansion of the universe carries that journey to its end. Space itself is growing, and the light crossing it is stretched and cooled as it travels, losing energy to the growing of space, exactly as the first light of the universe has been stretched into its faint, cold glow. So the warmth of the stars is poured into a room that is forever enlarging, a room that grows faster than the warmth can ever fill it. The heat can never gather, never pool, never warm the whole, because the whole keeps getting larger. It can only spread and thin and cool and drift outward into ever more space until it is shared so evenly and so faintly across so much emptiness that it is everywhere at once and warm in no single place. Seen across the longest spans of time, this is the universe's slow and patient direction. Energy spreads out. Sharp differences soften. The hot grows cooler, and the cold grows ever so slightly warmer, and everything drifts across unimaginable stretches of time toward a single faint and shared temperature. There is no need to find this sad. The stars will burn for a very long time yet, and the sky will be full of fire for ages beyond counting. But the long direction of things is toward evenness, toward a universe that has shared its warmth out so completely that the warmth and the dark become nearly the same thing. The cold of space and the heat of the stars are not enemies. They are two ends of one long, slow, gentle process. The universe quietly giving its warmth away into the dark, one star at a time, across all the ages there are. Part 14. The quiet answer. We have come a long way out into the dark, and we can gather everything now into a single, calm understanding. Space is cold, and the stars are hot, both completely true at the same time, and there is no contradiction hidden in it anywhere. There is only the consequence of a few plain facts, followed patiently all the way to their end. Temperature is the motion of particles, and space is very nearly empty, so it has almost nothing in it to be warm. Heat can cross the emptiness only as light, and light spreads out and thins as it travels, so the warmth of any star fades to a whisper only a little way out from it. Things adrift in the dark lose their own warmth, the only way they can, by glowing it slowly outward, and they settle toward the faint background warmth left over from the beginning of the universe, a few degrees above the absolute cold. The stars are furnaces, but they are small and very far apart, islands of fire scattered across an ocean of dark. The fire is real. The cold is real. And across almost the whole of the universe, the two simply never touch, because between them lies almost nothing at all. There is a comfort in this, once it is understood, that is worth carrying with you as the night settles. The cold of space is not a force reaching in to find you. It is not a wind, not a presence, not anything that wants anything. It is only stillness. It is only emptiness. It is only the quiet absence of the rushing motion we call heat. The stars burn in their distant places, and their warmth spreads outward and softens into the dark, and almost everywhere the universe simply rests in a great, even, patient cold, held just above the absolute bottom by the last faded light of its own first morning. There is nothing frightening in that picture. There is, in the end, something deeply peaceful in it. Think back over the road we have traveled tonight, gently, without straining to hold it all. We began with the smallest thing, the trembling of particles that we call warmth, and we found that cold is only the slowing of that trembling, the quiet that remains when the motion drains away. We learned that warmth can cross the emptiness of space only as light, that 2 of the 3 roads' heat travels close completely in the vacuum, and that the one road left open lets warmth spread and thin until it fades to almost nothing. We watched a star's light fan out and weaken with distance, watched warm things glow their heat slowly into the dark, and found at the bottom of all that cooling not a perfect zero, but the faint, ancient warmth of the universe's first light, holding everything just above the absolute floor. We saw the coldest places, the dying star's breath, and the shadowed crater, and the chilled clouds of a quiet room. And we saw a spacecraft living at 2 temperatures at once, scorched on one side and frozen on the other, with nothing between them. We climbed the ladder of our own sun from its furnace center to the cold shore where its wind gives out, and we followed the heat of the stars to its end, spread thin by distance, handed off to drifting dust, and stretched cool by the growing of space. And at every step we found the same simple thing underneath, that hot and cold are only the gathering and the spreading of motion, and that space is cold because it is empty and enormous, and the fire within it is gathered into tiny scattered points. So when you look up at a sky full of fire and remember that the dark between the stars is colder than any winter, you do not need to feel the cold of it. The warmth that matters is close and small and yours. It is the warmth of your own body, your own quiet corner, the gentle heat that gathers around you where you rest tonight. The immense cold of space asks nothing of you and reaches in for nothing. It is simply the way the universe spreads its fire thin across the dark, far away, where it can do you no harm and ask you no questions. And so we leave the stars to their burning and the dark to its stillness, 2 ends of the same long and gentle story, the warmth spreading outward, softening, and settling at last into a cold so even and so patient that it has held the whole universe for ages without complaint. Nothing out there is reaching in for you. There is only the quiet and the faint old light behind it, the first light of everything, still glowing, ever so softly, in every direction at once. Let your breathing slow. Let the warmth of your own small corner hold you gently. There is nothing left to solve and nothing left to carry. Sleep well, and good night.